Hello. Yeah, good evening all. Can you please confirm whether am I audible or not? You can type in chat box. Yeah, I guess my voice is reaching to you. So let's start with our session today. So good evening all. My name is Jitraj Singh Sujal. I'm Prime Minister's Research Fellow in Department of Earthquake Engineering from IIT Roorkee. I'm currently working as a research. Currently working as a teaching assistant, additional TA for this NPTEL course, which is NOC 25 C115 Ground Improvement. This course is currently being tutored by Professor Dilip Kumar Bedia, who is professor in Department of Civil Engineering from IIT Kharagpur. So before starting with the session, those who are joining this session for the first time, let me tell you. So what are the objectives of this session? So these sessions are particularly meant to interact with our learners. We'll be discussing some of the important concepts which will be required to solve the assignment problems. Also, we'll be solving some of the sample questions which are related to that week particular assignment question. We will be involved in the doubt solving session, and apart from that, if you are having any other technical query related to the course, feel free to reach out to them. So let's start with our session today. So here is your first question. Uh, so there is a process which is associated with the removal of the air from the void spaces of the soil mass. What is that process known as? Yeah, so let's check the answer. The answer for this corresponding question is, yeah, it's compaction. So whenever there is a process which is associated with removal of the void space, and if that voids are concerned with the air voids, then we call that process as the compaction. As if there is associated with the removal of the water from the void, so there is a dissipation of the excess pore water pressure, and we call that pressure as a consolidation. This is second question in front of you. So if you don't have anything to discuss concerning with the first question, let's start with the second question. So due to the compaction of the soil, what is the particular process is associated? So let's check the answer. Yeah, answer is C. That is the decrease in the future settlement of the soil. So let's see how does it work. So when you are having a particular soil matrix associated with your soil bar, so due to the compaction of the soil, what you can observe, there is a uh, removal of the air voids from the soil matrix. So you can see there is a compression in the soil. So due to that compaction, whatever settlement which need to be occurred, the maximum of this has already been happened. So in that case, your compaction of the soil mass is occurred. So you can observe there is a decrease in the future settlement of the soil, because whatever settlement which is about to happen, it has already been happened. So the correct answer is C, which is decrease in the future settlement of the soil. Uh, Saturation is the essential condition for. So any doubt with question number 2? If not so, then we can move to question number 3, which is saturation is the essential condition for which of the given part. So there is a question on the screen right now. So you need to select one of the probable option for that. So the question is, saturation is the essential condition for which of the particular phenomena. Let's see. So let's check the answer. Yeah, of course, among all those four options, because usually for the compaction, you don't require your soil to be saturated. In that case, even the soil is totally dry and unsaturated, you can uh, not unsaturated, but it's totally dry. Then you can go for the compaction process. And but when there is a water which is available in the voids, then it will correspond to the consolidation phenomena, which is basically the removal of the excess pore water pressure. So that is B is the consolidation. Moving to next question. So question number 4 links with the influencing factors for relative compaction are. So what are the associated influencing factors for the relative compaction. So let's check the answer. Yeah, so the correct answer is for the relative compaction, it depends on all the three mentioned entity. So first is the like how your geometry is there, so that depends on the type of geometry as well. Then second depends on your moisture content, like how moist your soil is, and also which compaction method you are taking into account. So all this influencing factor will account for like how much compaction you want to achieve. So the correct option is option B, which is all of the above. So let's move to question number 5. Uh, so the optimum moisture content of a soil is 17% and its
Moisture maximum quantity is 17 for specific gravity. Theoretical density of OMC
yeah. So you have been given with a question. The OMC of the soil which is given to you is 17%. The maximum density of that soil is 16.7 kilonewton per meter cube. The specific gravity of the soil is 2.7 and the theoretical dry density at OMC corresponding to 0 air voids is. So you need to find out how much is the theoretical dry density at OMC corresponding to 0 air voids.
optimum moisture content.
One second, guys. I need to restart the presentation again. I'm once again repeating the question. So the question which is given on the screen right now is the OMC of the soil is 17% and the maximum density is 16.7 kilonewton per meter cube. The specific gravity of the soil is 2.7 and the theoretical dry density which you need to achieve at OMC corresponding to zero air void is. So unit weight is given to you. So you just need to use the simple geotechnical formula for finding this answer. Let's check with that. I'm so sorry. Yeah. So do we have answer with us? Okay. Let's wait for 1 minute and then we will solve this. So let's check the answer. Answer is 18.1. So you have been given with optimum moisture content, which is 17%. The maximum density is given to you as 16.7. The specific gravity of the soil is 2.7. So you need to calculate what is the theoretical dry density. So we know gamma dry is G gamma W upon 1 plus ES. ES can also be written as G gamma W 1 plus E is your WG, where W is your moisture content. G, which is given to you, is 2.7. Gamma W, which is given to you, is 9.81. Then you have 1. Then again 2.7. And if I put water content W, so it's 0.17. So here is the answer. 9.81 into 2.7 divided by 1 plus 2.7 into 1.7. So the correct answer is 18.15. Yeah. So we are having the answer. which is 18.1. Let's move to question number 6. So in a compaction test with increase in compactive effort. By the way, any doubt in question number 5? If not so, then let's move to our next question. Question number 6. So in a compaction test with increase in compactive effort, uh, both the maximum you need to select which of the correct option is. So both the maximum dry density and the OMC content increases, both the maximum dry density and the OMC content decreases, the maximum dry density increases but the optimum moisture content decreases, the maximum dry density decreases but the OMC increases. You need to select one of them. So let's check the answer. Yeah, so the correct answer is option C. So let's say how it's working. So usually if we see the plot where we need to analyze like how much compacting effort we need to make, So on the one axis you are having a dry unit weight, and then you are having 10, 12, 14, that will go up to 24. Okay, so this one is your optimum moisture content. So if we see, usually the plot between the dry unit and the optimum moisture content is inverse parabol is this inverse cup shape uh, profile. So as you move upwards with the dry unit weight, you will see your compacting effort increases. So as your soil becomes dense, so that's how your nature of the dry unit weight versus OMC will look like. So you will observe that with the increase in the compacting effort. So here there is a increase in the compacting effort because your soil is becoming more dense. So in this particular case, what we are basically observing, with the increase in the compacting effect, your dry unit weight is increasing, but at the same time your optimum moisture content is decreasing, right? So that is how the things are happening. So if we see like which option basically represents this trend, so here is this thing. So the maximum dry density increases but the optimum moisture content decreases. So your option C will correspond to the correct answer. Let's move to the next question. So question number 7. By the way, any doubt in this? Yeah, if not so, then let's move to question number 7. So we are having four different geomaterials which are compacted at the same compacting effort in the field, which will represent the correct sequence in the increasing order of their maximum dry density. Yeah, so let's check the answer. So the correct option is A. So let's check what you guys have given. Yeah. So yes. So let's check how it is. So if we usually check in all the four options, we are having the four type of geological material available with us. First is the clay, then you are having a silty clay, then you are having a silty sand, then you are having a well graded sand. So among all these four options, if we see, uh, we can see that the well graded sand among all four of them will have a higher dense packing, and that's why it will correspond to the higher maximum density. Then you are having the next material is the silty sand, because since you are having a silt content, so you can expect lower density as compared to the well graded sand, but at the same time you are having the clay material here. So this clay material basically will correspond to further decrement in the density, so clay and the silty clay. So and since you are having a silt content in that, so you can expect a higher density in this case, as well as for the clay it's low. So the correct option among all four is this. You are having the clay, silty clay, then silty sand, and the well graded sand. So some of you have given this answer correct. So yeah, it's intuitive. So any discussion you guys want to have on this? If not so, then let's move to next question. So you have been given four type of tests, and you need to determine what all those four type of tests are corresponding to which parameter, whether it's penetration index, stiffness, moisture content, density, how they are linked with each other. let's check the answer. Yeah, so the correct answer is option C. Okay, I think it again got stuck. Yeah, so the correct answer is option C. So let's check. So sand cone method, if we see, this is a very famous, like popular method to evaluate the in situ density of the soil. So usually you are having a certain setup which is available there, and then you take a known weight of sand sample into that particular flask, in that particular flask, and then you take it to the site, and then you pour that sand material uh, to the pit which has been made at the site where you want to evaluate the density. So that density which we are calculating, like using the sand material, so that density of the sand material is already known at prehand. So that's why the sand cone method is utilized to calculate the density. So definitely the A option you can link it to the form. Then when you are going for B, which is the dynamic cone penetrometer, uh, so dynamic cone penetrometer is basically again a in situ field investigation technique where you basically insert a cone which we into the soil, and as that cone is penetrating into the soil, it will basically relate the tip resistance of that coin and the skin friction of that coin to certain density parameter, and we correspond that to as the penetration index. Then you are having C, which is the falling weight deflectometer. So in that particular case, you want to evaluate the density of the soil at the site. So basically you allow a certain vehicle to move at the site, and for the known weight of the vehicle movement, you measure how much the deflection has been taking place, and using that falling weight deflectometer you calculate the stiffness. Then for the time domain reflectometry, basically it is utilized to calculate the moisture content. So in that particular case, basically you allow a certain waves to pass through a soil medium, and then you basically check the reflection of that soil waves, and now you know how much time it took for the waves to travel from one point to the another point, and you also know how much distance is between them. So using the help of that, you can uh, calculate the velocity, and Using that velocity, you can relate it to the dielectric constant of the soil, means the resistance of the soil, which will basically help you in relating that thing with the moisture content. So again, yeah, D is the three. So yeah, the correct answer is option C. Any doubt in this? So one by one, you can check each and every method. Uh, so some of are widely used, and this time domain reflectometry is based on the uh, wave reflection phenomena. So where you basically allow a wave to pass through a particular soil medium, you allow the calculate you calculate how much time is required to cover a particular length, and then using that you calculate the velocity, and then you back relate that velocity with the dielectric constant of the soil, which will basically give you the moisture content. So moving to the question number 9, this is there in front of you. So soil has been compacted at a dry side of the optimum moisture content as compared to the wet side of the OMC has. So you are having soil which is one at the dry side of OMC and one is the wet side of the OMC. Uh, so how you will relate that dry side and the wet side of the OMC with the shear stress? let's check the answer for this. Yeah, so if we check, soil compacted at the dry side of the oil tree as compared to the wet side of the oil tree is having the more shear strength. So you are having a dry density, and then there is a optimum moisture content. So if you take the plot of this, so here basically your optimum moisture content lie. So here is the moisture content. So here is your moisture content. So this is your oil seed. So here you will be having a wet side, and then here you will be having the dry side. So definitely at the dry side you will be having the less moisture available in the soil. So that's why due to reduction in the uh, dry side, you are having the less water content available, and that will correspond to the higher internal friction in the soil particles, and that's why it will lead to the more shear stress. So that is the part. So let's move to question number 10.
Sir, have a query.
Yeah, please.
Is it due to lack of lubrication at the dry side, the shear strength is more?
Yes. So
Yeah, that's it.
yeah, yeah. So means due to the less water content, you're definitely the effective stress is high, and the shear strength is a function of the effective stress. If you see the usually the Moore Coulomb friction criteria, so in that case your shear strength is a function of the effective stress, and since due to the less water content your effective stress will be high, and that will correspond to the higher shear strength, and that's why at the dry side you can observe like your soil is having the more shear strength. So that is it. Okay, then let's move to question number 10. So in question number 10 you see the in situ void ratio of a granular soil deposit is 0.5. The maximum and the minimum void ratio of the soil are determined to be 0.75 and 0.35. GS is 2.67, gamma W is 9.81 kiloliter per meter cube. Now what is the relative compaction of the deposit is? So the in situ void ratio is given to you, the maximum and minimum void ratios are given to you, GS is given to you, gamma W is given to you. Now what the relative compaction of the deposit is? Yeah. So do we have any answers? Okay. Okay. Yeah. Let's check the answer. Yeah. So the correct answer is option B. So let's check with this. Yeah. So the in situ void ratio is zero point 0.5. Your maximum void ratio is 0.75 and your minimum void ratio is 0.35. Your GS value is 2.67 and your gamma W is 9.81 kilometer per meter cube, right? So your relative compaction is basically given by your gamma in situ to your gamma minimum. Your gamma in situ is basically G gamma W 1 plus E in situ G gamma W 1 plus ES, right? Yeah. And G gamma W 1 plus, yeah, so 1 plus in situ. And then your gamma minimum is given by G gamma W 1 plus E minimum, right? So your relative compaction is basically 2.67 and gamma W is 9.81. 1 plus E in C2 is given by 0.35. Then your G gamma W, which is 2.67, gamma W is 9.81. Then you are having 1 plus class yeah, so you are having 1 plus E minimum. Your E minimum is, yeah, so gamma, Okay, relative compaction is gamma in situ to gamma max soil. So you want to compare how much is your maximum density, and then corresponding with that you want to evaluate how much your in situ density. So gamma in situ is your G gamma W 1 plus E in situ, and then your gamma maximum will correspond to your E minimum. So your E minimum is 1.35 and your E in situ is 0.5. So that's how you need to compare. So if we take this, so that will come out as 1.35 upon 1 plus 0.5, that is 1.35 to 1.5, which is basically your 9 by 10, and that is zero point 0.9 in percentage. If you see, that is basically your 90%. Yeah, so the correct answer is D, option D. So the relative compaction of the deposit which is given to you is the 90%. So that was the part. Any doubt in this, guys? So it's straightforward. You just need to know what is the relative compaction formula is. So that's basically your ratio of the in situ density to your maximum density. Your in situ density you can evaluate using the G gamma W upon 1 plus E in situ, and your maximum density basically you evaluate using the G gamma W upon 1 plus E minimum. You can take the ratio for both of them, and that will basically give you like how much is your relative compaction is, which is corresponding to your 90%. Any doubt in this, guys? So yeah, we do got some correct answer. Yeah, that was the gamma maximum. Thank you for pointing out. And then let's move to question number 11 if you don't have any doubt in this. Yeah, so again that's a theoretical question in front of you. So where do we use the vibratory rollers for compacting? So the vibratory rollers are suitable for compacting. So which type of soil will you suggest the vibratory rollers are used for? let's check the answer. The correct answer is option C, which is sand and gravel. So the vibratory rollers are suitable for compacting. Yeah, so the correct answer is C, sand and gravel. So usually we go where we want to increase the density of the soil, where this is being done by arranging the interparticle packing of the gravels and soil masonry, and that is has been done by the sand and gravels. So the vibratory rollers are suitable for the company for which thing, which is the sand and gravels. So let's move to the next question, question number 12. So in question number 12, you are having the shift foot rollers are more effective in compacting clay soil because of. So why the shift foot rollers are more effective in compacting clay soil? You need to select one of the options. Yeah, so the I want to repeat the question. So here the question is the shift foot rollers are more effective in compacting clay soil because of which of the option? So yeah, let's check the answer. So the correct answer is option B, which is that the contact pressure is high. Though the shift foot rollers are more effective in compacting, uh, is naddling action same as contact pressure? Mm, so
No, I meant to say is needling action. Uh,
okay, needling action. Yeah, so that's what we are saying here. So because of the uh, smaller surface area and due to the more mass accumulated to that uh, uh, sections of the roller. So yeah, when you are saying the shift foot rollers, so that needles which you are saying, yeah, that is relating to the contact pressure. So due to that, the contact pressure is high. Whether am I clear or not? So I think you are talking about the shift foot rollers, where the rollers are having the uh, you know some sections which are coming out of the rollers. So are you pointing to that, right? The needling action.
it does have a sheep foot like projections coming
Yeah,
over.
yeah, yeah, yeah.
They typically press it. Is that same as that of the higher contact pressure?
Yeah, so we are basically linking to that only. Yes, you're correct. Yeah, so due to that part, because if you would have seen the sheep foot rollers, so there are some parts, sections which are coming out of the roller. So that's we are saying as the sheep foot roller, and that is corresponding to the higher contact pressure. So yeah, so the contact pressure is high, and that's why it's more effective in compacting place. So yeah, that was the question number 12. And then let me present it again. So let's move to the question number 14. So I think I have like the sequence which I have marked, it's a bit wrong, but yeah, you can consider it. So in the laboratory compaction test, the OMC content of soil. So what basically happened to the OMC content of the soil when we take it to the laboratory compaction test? So we need to select one of the phenomena. So again, if you know how that plot works, you can answer this question. So let's check the so let's check the answer for this. Yeah, so the correct option is option C. Why so? So we know if there is a graph, so you are having this optimum moisture content, water content, and then you are having the density. You are having the optimum moisture content here. So with the at the less or dense soil, your this OMC curve will happen something like this, right? So as the OMC is decreasing, there is this uh, type of soil where the relative density is increasing. So here you can expect like there can be more, like the grains can be more coarser, as well as here you will be requiring the more density. So these curves, if we see how the trade flows, so it will basically moves away from the optimum moisture content. So like so here we can see here the compaction energy is also increasing to densified soil, and as well as the grain is also become coarser. So yeah, so sorry. So I think there's a issue with the option. So with the increase of both the compaction energy and the force grain energy, so that is the decrease. Sorry. So the correct answer is option C. Any doubt in this? If not, so that let's move to question number 15 to 16. So you are having a 1 meter wide square concrete footing which is designed to be embedded at a depth of 1 meter. The site has at 8 meter thick soft clay soil from the ground surface and underlain by very dense sand layer. The groundwater table at a depth of 0.5 meter. The unit weight of the soil above the groundwater table is 19 km per meter cube and below groundwater table is 21 km per meter cube. The column load applied to the footing is 161 kilonewton and the concrete unit weight is 24 kilonewton per meter cube. Assume the unit weight of the water is 10 kilonewton per meter cube. Uh, what is the applied pressure at the base of the footing is? So yeah, we are having two different answers. Do you guys want to comment upon this? Like, how did you approach to this question? How did you approach to this question? So any one of you, like
Yeah, I have taken the total load and self weight and
self,
divided by the
yeah. So self weight of footing.
concrete, yeah, footing,
Okay,
and divided by the area
okay.
base.
So how much answer you got?
Around 174, 173.
Okay, the answer is 180. And what about you, Abhirami, if you want to share? Okay, you are getting 185. Okay, so let's have a look on this. So you are having a 1 meter is designed to be embedded at a depth of 1 meter. Okay, so this is your footing which is embedded at depth of 1 meter. The site has 8 meter thick soft clay from the ground surface underlined by a very dense sand. Okay, the groundwater table at a depth of 0.5 meter. Soft clay layer, right? And this the unit weight of the soil above the groundwater table is 19 kN per meter cube, and below groundwater table is okay. So your groundwater table is this. So you are having 19 kN per meter cube. Okay, and below groundwater table is your 21 kN per meter cube. The column load which is applied to the footing is 161 kilonewton, and the concrete unit weight is 24 kilonewton per meter cube. So they haven't given the dimension of this thing. Okay, so okay, we are assuming that this 161 is directly getting transferred here. So that is 161 kilonewton. Now, do we need to consider this weight of the soil also? That is the part. Okay, so if we take 24 kilometer per meter cube, so in this case, the volume of the con footing is, so they have given the dimension square footing, so 1 meter by 1 meter, and okay, and also they are saying the depth, so they haven't given the thickness, so that is the part. So yeah, if you assume that the whole footing is 1 meter depth, is embedded at a depth of 1 meter, so that doesn't mean your whole footing is of 1 meter depth. So the unit weight of the soil over the groundwater table is 19 kN per meter cube. So you are having this 1 meter, 1 meter, and since the thickness is not given to you, and also the dimension of this column is not given to you, like how much it is, right? So it becomes difficult to identify. So the question seems incomplete. again, if you take the assumption, let's assume that this column is not participating that much, and you only take the overburden of the soil which is available at the top. So you don't take unit weight of this thing into account. So you are having the 161 kilonewton, and then I'll just take the unit weight which is coming from this. So you are having 19 kilonewton per meter cube, which is acting for a depth of 0.5 meter, and let's say it's having a dimension of 1 meter by 1 meter, so that is corresponding to a volume. Then you are having 21 kilonewton per meter cube, but below ground water table. So again we need to subtract 10, and that is again 0.5. So how much that will turn out? 161 plus 19 into 0.5 will give you 9.5, and then 21 into 0.5 will give you as 10.5. Sorry, so 21 minus 10 is 11. 11.5 is 5.5. So how much is this? So this is 161 plus 14 plus 15. So that will turn out as 176. Yeah, so it's near to 174. Okay.
Sir, actually, your approach is also correct
Uh-huh.
because it's a vague. The question is a bit vague.
Yeah, yeah. So we don't have the clear indication. So again, it depends on the designer. So what you will take into account. So okay, if that would have been theory, so you need to mention the assumption, like since we are not considering the column unit self weight as well as the thickness of the footing is very minimal, such that its weight is not contributing. So you can then just take the overburden of the soil which is coming over the footing, as well as the 161 kilonewton column load which is coming from there. So I think we can go with any of the approach. Whatever you guys have considered can also be right. But yeah, we need to make the assumption, mark the assumption wherever we are solving this. So yeah, that's how we'll approach this question. It's having different ways. So let's skip 15 and 16 for the time being. Uh, so it's also having the same thing, the effective overburden stress at the base of the footing. So you can calculate overburden stress, so that's not a big deal. Then let's move to different question. Yeah, so here you can see you are having a GWSE represent the step specific gravity water content void ratio. If gamma W represent the unit weight of the water and the gamma D represent the unit weight of the soil, then the equation of the zero air void depth. So you need to represent how you will represent the equation of the zero air void depth. Okay, so we are having gamma D, then you are having optimum moisture content. So usually uh, if we look into this, that's how your plot is, and your zero airport line will look something like this, and your all the curves corresponding to the graph lie here. Now here you need to represent how you represent this line. So usually for the dry density, you know, the formula is given by gamma d g gamma w 1 plus e, right? And for zero air void line means there is zero air voids, so all the voids are filled with the water. So in that case the soil is fully saturated, so your S is 1. So we know ES equals to WG. Your S is 1, so E is equals to WG. So your gamma dry density then will be represented by G gamma W 1 plus W. So that's how your thing will look like. So gamma W G gamma W upon 1. So the correct option is option B, G gamma W 1 plus W. So the question number 17 is having correct answer option. Yeah, so I think we are over with the time right now. So I think we can end our session today. If you guys are having any question, please feel free to ask. Else we can meet on next Tuesday.
Yeah, the x-axis is water content, right?
Yeah, sorry. X-axis is water content, and this is the water content. Sorry for the writing. This is your water content, and then this is your of your moisture content. I'm so sorry. Yeah. Anything else, guys?
Yeah.
Okay. If you don't have any other query, then I think we can wind up our session today. I'll be uploading this video on YouTube, so you can ask your queries on the YouTube comment section. Those who are watching this video at the latest stage, and we can meet on next Tuesday at same time at 6 p.m. Thank you so much for joining. Yes, Shiva. Do you have anything?
No, no, that's it then. We'll meet next week.
Okay, okay. Then let's meet next week. Thank you so much for joining. So, yeah. So, when we're talking about the literature, so what are the design modifications?